Hello and welcome to this video on our work on situational aware model refinement for semantic image segmentation. This work was done jointly by the Technical University of Munich and the Fraunhofer IKS also in Munich. My co-authors were Markus Hofbauer, Joao Witosaki, and Christopher Kuhn, and my name is Lukas Habermeyer. And today I'm going to introduce you to a new idea of a situation aware refinement method for, in this case, semantic image segmentation. So for any autonomous system, it's crucial to understand and perceive the environment as precisely and as accurate as possible. But this accurate environment representation is highly dependent on external factors such as rain, fog, etc. And existing research is mainly focusing on the model architecture to squeeze out the last bit of performance. And there is a insufficient awareness of the operational environment where your autonomous system is moving in, such as weather, infrastructure, or other road participants. And that arises the question how one can quantify these effects on the sensing capabilities of your autonomous system. And we argue that a systematic refinement approach can help here. Let's first have a look at existing works out there. First of all, there's the proxy dataset, which is a synthetic dataset with different influencing weather conditions recorded in the Carlo simulator. Based on this dataset, they increase the segmentation performance and also the segmentation robustness. Second, there's the idea of a model-centered assurance approach, where you can guarantee for the absence of systematic faults. And this guarantee can be done by the usage of simulation data. And third, there's the Carlo Open Driving Simulator, which is well known and heavily used in scientific research. So how does our idea of a situation where model refinement looks like? So you start with a semantic segmentation model, and then you put this semantic segmentation model into the refinement stage, which is indicated by the box here. Then you test under varying external factors. Based on these tests, you can determine the harmful factors. And once you know the harmful factors, you can collect new data under these harmful factors or conditions. And once you have this new data, you can add it to your existing data set and fine-tune your model. Then you go back to the first stage and you start all over again. In our case, we fine-tune a pre-trained deep lab version 3 architecture. Then we generate new scenarios and replay these scenarios with changing external factors, which can be easily done by the Carlo driving simulator. And then we analyze the influence of external factors on the model performance. In detail, this workflow looks the following. You start with the semantic segmentation model. In our case, it's a deep lab version 3 pre-trained already. Then we choose a new deployment situation. And for this, we generate new data in simulation and fine-tune the model to this new deployment situation. Once we've deployed our model, we generate new scenarios with changing external factors. And for this, we have the replay capabilities of Carlo. And we record a scenario. And once we've recorded the scenario, we replay this scenario with varying traffic, weather, and daytime conditions. Once we have done this, we get the model performance for each of these replays recorded in the stage before. And once we have the performance of the model in each of the replays, we map the external factors to the performance in each of the replays. Our experimental setup looks the following. As I said already, we have a deep lab version 3 model architecture pre-trained on 5,000 images collected in Carlo's default map under dynamic weather conditions and dynamic traffic conditions. Then we fine-tune the model on 400 images recorded in Carlo's Time 2, which is this deployment step I was showing before, under dynamic weather conditions and dynamic traffic conditions. And for the replays, we've chosen two scenarios. The first scenario is the urban canyon scenario. You can see here. And the second scenario is a residential area scenario you can see on the right side. So basically, the urban canyon scenario is a classical urban canyon where you have houses on the left and on the right side, and the car drives through this canyon. And for the residential area scenario, you have some wider sidewalks and you have some trees, etc. To evaluate the model performance, we have two methods. First of all, we have the mean average intersection over union, which is the average of the intersection over union for the drive through the urban canyon or the residential area. And secondly, we have the visualization or the visual inspection of the images or the segmentation results. Based on the performance of the model in each of the replays, we calculate the correlation between the external factors and the model performance. For the external factors, we were defining 10 replays. So for instance, replay 0 would be a drive through an urban canyon or through a residential area with clear conditions at noontime and with no road users. But on the other side, we have, for instance, replay number 8, where we have 60% fog density, nighttime, and a lot of road users. Based on the mapping of external factors to the model performance, we can perform our correlation analysis. And for this, we plotted the correlations of each of the external factors to the mean average intersection over union. So as you can see, the heaviest negative influence has the precipitation, which is the rain density. And also there is some influence of fog density, the number of vehicles, and the number of pedestrians. For the residential area, you can see that fog density has the highest influence, the highest negative influence on the mean average intersection over union, and therefore on the model performance in the residential area. Based on the results of the correlation analysis, we determine our harmful factors. In this case, the harmful factors are fog density, number of vehicles, number of pedestrians, and precipitation, but we leave precipitation aside for the first time. In total, we have 6 models to compare. The first model is the baseline model. The second model is a model refined with fog. The third model is a model refined with road users only. The fourth model is a model refined with the intersection of fog and road users. That means that fog and road users are present at the same time. The fifth model is a model refined with the union of fog and road users. That means that we first took images of more road users, and then we took images of more foggy scenes. And the sixth model is a model refined with dynamic influencing factors. That means that we randomly collected new images in order to show that our approach is outperforming the others. Now it's time to compare the 6 refined models against each other. Those 2 plots show the performance on the left side in the urban canyon and on the right side in the residential area. On the x-axis, you can see the index of each of the replays. The last column gives you the average performance of all the replays. Same on the right side. On the y-axis, you can see the mean average intersection over union. For the urban canyon, one can see that on average, the model refined with the intersection of fog and road users is performing the best. Same holds true for the average in the residential area. Here, the model refined with the intersection of fog and road users again performs best. Astonishingly, you can see that both models refined with fog perform especially better in replays where heavy rain, which is number 3, is present. Same holds true for the residential area. A visual inspection underlines the results shown before. In the left column, you can see the input images. The second column shows the according ground truth. The third column shows the image segmentation results of the baseline model. The fourth column shows the image segmentation results of the intersection model, and the last column shows the image segmentation results of the randomly refined model. It can be clearly seen that the intersection model performs best in all three chosen input images. Road lines are exactly detected, and also some pedestrians are detected on the right side. Also, you can see that the trees are detected more precisely than in the random model. This is a total difference to the baseline model, which doesn't detect any car and no pedestrians. To conclude, we have shown the advantage of a systematic refined model over a randomly refined model. And in more detail, that means that our systematic refinement approach outperforms the randomly refined model by up to 10.6%. For further application, one could use the knowledge obtained during the refinement process in order to predict the model performance based on the external factors. Also, for future work, we want to find the optimal amount of additional refinement data, and we want to perform the refinement process in a finite granularity of external factors. If you have any questions, please feel free to reach out to me. You can find my contact address here. And thank you for your attention.